I don't know about you, but thank you, Ruth. I think this is really the coolest thing. I mean, seeing that stuff hot off the press from Historic Scotland is just amazing. So I work at a company that is a tool company. We're a software company. We make tools to help everyone imagine, design, and create a better world. And what better way than to do that, to apply those tools to historic preservation and what CyArk is doing. We've been supporting CyArk for a couple of years now, met them back at the TED conference, and was really moved by that story. So I want to share with you the tools. Where is this technology going? Where is it today? You know, if you think of this ability of technology tools to take three-dimensional data and bring it into a digital form from the analog world, it reminds me of the music industry and how the ability to digitize music and rip, mix, and burn that music really changed the way we enjoy music, whether that's the classics or modern. But being able to rip, mix, and burn atoms is really what we're talking about here at CyArk. And I call that, instead of rip, mix, and burn, rip, mod, and learn. So we're going to rip reality, take atoms, put them into digital form where we can model them, work with them, improve them, do analysis, get meaning from them. And then finally, the real goal of why we're all here is the learning that comes from that. How do we connect with the constituents of today and the future? So of course, Ben and friends who made the original CyArks, that was a really legendary device that could take reality, put it into digital form where we could work with it. And of course, not long after came CyArk. Okay, so if you think of this ability to take Mount Rushmore and capture that digitally, that was kind of a change in the historic preservation market, what you could do with this kind of thing. But if you look at 5 years later with CyArk, we're really up to about 100 of these sites scanned. And that's amazing, because if you think of the CyArk 500, we're talking about getting 500 sites in the same time that it took to do 50 to 100. And so are we going to get faster human beings to do this? I think the real solution here with the CyArk 500 is not faster humans, but we need better tools. And so I'm really excited about a lot of the research that's happening at a number of universities, a number of companies around the world, at our own as well, in the research of these tools. So just to put this in perspective, the 500 is critically important, the most important sites. But there are 981 UNESCO World Heritage Sites. There's over 55,000 different museums in the world. And if you take just one of these museums, the Smithsonian has 137 million objects in its collection, of which less than 1% are available for the public to see in any given year. So obviously, there's a major challenge here. And so what I'd like to talk about with the tools is how do we democratize the tools? How do we make these tools more available to historians and the public everywhere? And one role of that is the laser scanner itself. You know, since the CyArks, the accuracy has improved, the range has improved, the speed has improved. This has become more democratized because the hardware has gotten better. And hardware has a tendency to do that, just like any technology. But over the last 3 years, we've seen these devices also become more democratized through price. We're seeing devices now that are far less expensive than they ever have been in the past, and this trend is continuing. There's more devices. Just in the last 12 months, we've seen an explosion of new reality capture devices hit the market. So this ability for now everyone, even someone with an iPad, to capture reality is pretty impressive. But that's not the only way that we need to democratize 3D data. 3D data is hard to work with because these scans can produce billions of points. Those billions of points often require very, very high-end workstation computers that not everyone can afford. This is new technology that you're seeing in the marketplace where you can work with data sets that have every leaf on every tree, every brick on every building, but this isn't rendered. This isn't coming from a high-end workstation. This is real time on a laptop. So this ability to work with massive data that doesn't have to fit into RAM anymore. Another way that we can democratize access to 3D technology is in visualization. It wasn't very long ago that this is the way point clouds would look coming out of these scanners. Okay? Very accurate three-dimensional points that meant something to, say, an expert, much like an X-ray means something to a doctor. But that doesn't work for the common person. I'm going to show you this exact same data set now with today's technology. It looks like a photograph. There's no difference in the data. Same laser scan, just different technology, different tools. One other way to democratize access to this 3D data, though, is in reducing the labor costs required to capture a site. There are a number of reasons why it takes a lot of labor to do these fantastical captures, much like what Historic Scotland has done. This is a target, and if you're in the business, you hate these targets because you have to put them everywhere so that you can register and survey how these different scans are going to snap together to make a unified model. If you have a lot of occlusions, like in this space, it's not uncommon to have to put up multiple targets. In this particular view alone, there's over 25 of these targets put up. And if you're in the rainforest and you're 1,000 miles away from the hardware store, it's a little too late to find out that tape does not stick to a wet tree very well. And if your targets move even by a millimeter, all of your data is suspect. And on a common project, you might have several hundred scans. Each one of those bubbles is a different scan in this bird's eye view. And for each one of those, after it was scanned in the field, usually back in the office, that 5-minute scan turns into something like around an hour of processing to do Where's Waldo with those targets. You have to look in those scans, do Where's Waldo, and match them up to link the scans together to make the unified model. But again, this technology is democratized here, where here is target-free registration, where a user gives the computer a few hints about where the scan comes from, and now the computer is automating the registration process in a way that's more accurate than a human could do it before. So this takes the hour of processing in the office down to less than the scan time, so you can do this while you're still in the field and make sure you haven't missed anything before you get on the plane coming home. Another way to democratize this access to 3D capture is through better user interfaces in the tools. Traditionally, these software tools have been very hard to use and took a lot of training. Now, Scott at CyArk was working with a group that didn't speak English. And he, with these better tools and better user interface designs, we have a number of researchers working on user interface designs, as are other companies, have made these tools much easier to use where you can learn this technology in a day. And furthermore, we can reduce labor costs as well by using these autonomous robots. You can go in the morning, give it a plan of the site, and then overnight while you're sleeping, it can do hundreds of scans for you, automatically register them, and when you come in the morning, they're already posted to the internet for the entire world to see. But probably the most significant way that my team has been working on around reality capture and democratization is to take the camera that's in your pocket right now in your cell phone and turn it into a 3D capture device. Now, it doesn't work for every scene. It has its limitations. It's not the same as a laser. But the process is called photogrammetry. You take a picture of an object from several different angles. The computer analyzes those pictures and finds common features between them. And from that, it can infer what kind of lens you had and the position that the camera was in three-dimensional space when the picture was taken. It can then recreate that object by triangulation to make a 3D capture. And so this is the level of the technology that we had just 3 years ago. It was really cutting edge back then at being able to figure out where those cameras were in space when the pictures were taken and recreate this point cloud. But as you can see, the quality of the camera is nowhere near that of a laser, far less. But this, 3 years later, here are some photographs of a little statue on someone's dining room table. And I'll show you what is state of the art today. This is shipping and free, available to anyone. You can see much more detail, much denser reconstruction. And we'll zoom in here in a second. And you can see some of the detail of these captures just from photographs. So when you think of those hundreds of millions of objects sitting in museums, this is a new way to use the crowd, to capture this kind of data. So some of the things that people have done with this photogrammetry process is, captured things like this. You can capture a bug at very small scale. You can capture entire buildings at large scale. You can capture things underwater. The Scripps Institute has been studying the acidification of the ocean and the loss of coral reefs, and where they were having to literally kill these coral to bring them back to study their volume from year to year. Now, with 15 photographs, you can get 500,000 points that are survey accurate and do your measurements from that. We made this technology free and put it on the internet, and so the general public has been playing around with it. Now, they're not historians, so they tend to capture things like their dog or their dinner. But this idea of the crowd getting involved gave me this concept. I went out to the internet and used crowdsourced photos I got from Google for Notre Dame. And this is from a couple years ago. The quality has improved since then. But the idea of using tourist photos to recreate sites is a pretty interesting one. And then I met, of course, Ben and his story of the Bamyan Buddhas and this very sad story. And so I worked with Getty Images and Associated Press and several other agencies to get some historic photos that were taken in the 80s and recreate the Bamyan Buddha in 3D. Now, again, this is 3 years old. We can get much higher resolution today. And if anyone has any historic photos of this site, I would love to get my hands on them. But the technology that we have today is on the left. And still coming out of research, this isn't in the marketplace yet, it's on the right here. You can see that once you take the photos, the neat thing is the technology improves. So by going out with the CyArk 500 and scanning these 500 sites, it doesn't mean that we're done. It doesn't mean that we're limited by that quality. Just in 1 year, you can see with the same exact input data, the reconstruction gets that much better. We can now see the hieroglyphs. Now, I mentioned that photos aren't perfect. There are a lot of objects that won't work with a photo. Things that are shiny, transparent, and so on do not work in photogrammetry. They work much better with laser. But laser has its own problems with occlusion and speed. And so some of the research we're working on now is how to combine laser and photo together to take the best of both. Photos are actually higher resolution than laser, okay? But they have what I call brittleness issues, which the laser doesn't have. And so you can see at this site that we have the accuracy of the laser, but we have the detail of the photo. Geometry is just one way. This three-dimensional shape of things is what we're getting out of the laser and photo. But there are other types of information we want to capture and store from our objects, and that is the material properties. How do things look? And that BRDF scanner is something that instead of scanning something very large, scans something very small, about a square centimeter of material. And that's used in the commercial industry for recreating these faux images. One of these pictures is an actual kitchen that was photographed. The other is a digital creation that doesn't exist at all. And it was using that scanner to scan how the wood grain actually reflects light at a complex level that's used. Now, the movie industry has been using these BRDF scanners for a number of years. If you've watched any Hollywood film, you've seen actors like Jeff Bridges be made 30 years younger than their actual age using this technology. But these BRDF scanners that scan both shape and material information of how the skin reflects light are very expensive. You can imagine a setup like this costs about $1 million, and you have to bring the object to it. So we've been working with the French INRIA Institute, a research group, on some technology to do this material scanning, again, just using photographs, democratizing that. So taking a basic input image in a sky model, and then using our three-dimensional photogrammetry model to get a 3D map, and then decomposing how the light in the scene is working by doing rendering backwards. And that way, we'll be able to capture not just shape, but that same material that we have from a BRDF scanner. So that's the ability to rip, to capture reality into a 3D form where we have it. But we don't just want to store it away in a mountain waiting for World War III to happen. Really, the opportunity is to use that data today, to connect with our constituents and the public today. And that's where MOD comes in, this ability to model 3D and make meaning from it. So if we look at how the commercial world uses this modeling technology to make digital cities and do simulations of light studies, or whether you're doing an earthquake analysis on a skyway, something like that. The commercial world has been doing computer modeling, CAD models and CAD model simulation for a number of years. But again, it hasn't been democratized. Again, whether you're doing computational fluid dynamics and looking at weather flows and how they affect buildings, for example. So this technology exists at the very high end, but we want to democratize this as well. So in some of our research, what we're doing is taking these point clouds that are coming from the lasers and trying to recreate them back into a CAD model where simulations can be made far more easily and less costly. Or what we call perception engines. Here is a mobile laser scan of a roadway system that includes the trees and the grass. But putting this through a perception engine, having the computer automate the extraction of the important assets. So if you think of a historic structure, if you want to make a digital database, a record of where all of the important assets, every lighting fixture in this building, every stone, and so on, making that asset, this technology can automate and do what Google does for text, we can now do that with shape. So three-dimensional shape search. So imagine having catalogs of artifacts in a museum and being able to search on that kind of shape. Another way to use modeling is around finding differences in things. We heard about how the environment is really decaying and destroying many of our heritage sites. And so again, there's commercial technology that we can democratize where you take something like this pipe that is decaying over time because of stresses, and we can use that to find out how, say, a wall is going to fail so that we can mitigate that and try and repair it before it happens. There was a project that's a little bit secret, and I couldn't share you the visuals, but there's the delicate arches in Utah that are under stress and strain. And so we've done this kind of simulation on them and then done finite element analysis to do a future prediction as to when and how it's going to fail. And now the National Park Service is working to preserve those places. Another way is to take this digital data and create it in these models that can be used to actually change the shape, to get things back to what their original shape was after they've been degraded. So taking things like laser scans, creating CAD models that then can be pushed and pulled and, in digital form. Now, if you're trying to do this capture or get the data prepared in a way that you can do this CAD modeling, it once again is very, very labor intensive. This is kind of current process that some of our designers use when working with these artifacts. Not very easy, but that is kind of state of the art. So we have a research project which we're giving away free right now. It's called Project Memento. It's open to the public to play with this. And it allows you to take these photogrammetry scans that have been taken from photos, as you saw earlier, but then go in and do modeling on it. So change its shape, clean it up, select it, and improve on that object. Get rid of the defects in it. Here you could see preparing this scan that was done from photos and preparing it for 3D printing. So we'll select the object. We need to create a base. And here's some examples of some of those things. You can see the amazing detail. So very, very large amount of data in there. And when working with that large data, we need better ways of interacting with very large data sets that aren't actually a CAD model. They're just millions of triangles. So here you're seeing some research on smart selection. So just through some basic gestures, working with the computer in a more democratic way, in a way that's more human-centric and easy to communicate to the computer the intent that you have when you're selecting these complex 3D objects. So that's some research you'll see in the future. We're also working with the Smithsonian Institute on how to make these models to bring them alive. This is a laser scan of the cosmic Buddha, one of these signature assets that the Smithsonian has. And it's very accurately reproduced. I've seen the Buddha, this is what it looks like, and this is a 3D model. But the beautiful thing of when you have a computer model, being able to augment it allows us to see this. It's the same data viewed through different rendering software. And so now you can see the story in much more detail than you could before. Another thing that we can do, again, I know that Historic Scotland, they have a mission to make their historic buildings sustainable. And one of the problems with that is getting computer models that you can do sustainability analysis or simulation on. So we've been working with some drones, taking pictures from the sky, capturing the photos, making a three-dimensional model of a building, and then running it through a green building simulation software that runs in the cloud. So this software can tell you whether you should replace the windows or put in more insulation in the roof or what have you. What are the different ways to make this a more sustainable building? So we've ripped reality. We've put it into a CAD form where we can model it and simulate it and improve it and understand it better. But the real goal of the whole thing, of course, is around education. Okay? So what are some of the things that are happening in that space? At one level, I think of this education effort is really around storytelling. And I'm lucky enough to work at a company where we make these tools that service Hollywood. So the last 18 years, every Academy Award winner for special effects was using our tools. And if you've seen any of these films, you've seen these wonderful storytelling devices. But these devices can be applied to historic preservation. And so this is some of the things that really excite me, is how we can take this 3D data that CyArk is capturing, and places like Historic Scotland are using this technology tool that's coming from Hollywood and reapplying it to educational materials instead of just fantastical people shooting each other in space. So something with some meaning. So we want to democratize these Hollywood tools as well. One person doing that is Louise Leakey and the Leakey family of fossil hunters in the Turkana Basin of Africa. Now, if you go there, and very few people can because it's not an easy place to get to, they have 20,000 artifacts sitting in their vaults. And some of them are so priceless you need a special permit. They're in a locked vault that the Kenyan government has to give you in order to get access to one of these skulls. So even if you're a scientist in the field, there's many of these specimens that you will never see, you will never touch as you study them, let alone the public. But if we want to make the public be able to learn from this, Louise has been taking some of these artifacts, using photogrammetry to get three-dimensional models of these, and then more importantly, turn them into storytelling. So using some of the rendering tools from Hollywood to talk about the cranial ridge, how it evolved over millions of years as our diet changed and the muscles and how they attached to that ridge changed over time. And this is a great way to engage with students in digital form. We've also been working with her on a website to make it searchable, to take all of this data that's been captured so that you can search on it and index it, get more information about a specific specimen, or of course, see it in 3D. But it doesn't end there, because 3D on a screen is kind of removed from the object. So what I'd like to share with you next is, again, something that happens pretty routinely in the commercial world, which is 3D printing. So you take a CAD model, you have one of these $250,000 3D printers, and you print that device comes out of the printer already assembled, okay? But it hasn't been accessible until the last couple of years. Now, 3D printing, you've read in the news, there's over 75 different materials that you can 3D print today, and people have 3D printed clothes, they've 3D printed drugs, 3D printed food, 3D printed this car, 3D printed a sneaker, 3D printed organs. This is a stem cell 3D printer that prints ears and bladders and livers. And 3D print DNA. You can 3D print the Earth with LandXML, TopCon, and some others work on this kind of stuff. But more exciting for historic preservation are things like what Professor Kushnevis is doing at USC, where he's 3D printing buildings. Okay, so you take this is a prototype, a concrete pump, you put the 3D CAD shape in there, and it prints it. And again, the complexity of the shape is free when you're dealing with 3D printing. So if we think of some of these structures that we capture today with lasers, they will crumble, they will decay into the future. But wouldn't it be neat if a future version of this technology could 3D print that entire structure at near original quality? But again, democratization. These 3D printers now that we have some that are $250,000, not very accessible. That device there is about $1,000. And so consumer 3D printers are pretty interesting. Cosmo Wenman is an artist who's going around to the museums of the world, and he's mainly focusing on these Greek sculptures, doing photography, creating 3D models. And these sculptures are 3D printed on a MakerBot $1,000 printer. And he has a special process where he glues the pieces together and then makes them look like they're the original bronze or different kinds of metals. He actually has a process where he can make them into bronze. So starting with a $1,000 printer and arriving at a bronze reproduction. And much like how posters can popularize the artifacts that are in the museums and draw people in because they become familiar with it, the kind of stuff that CyArk is making available on its website to really educate people is really going to excite the public to travel and come to the original site. So we really applaud some of the things that Cosmo has done. And of course, copyright and intellectual property are an important part of this, but he only works with things that are out of copyright. That's one way of doing reproductions, is 3D printing, but there's other standard types of manufacturing processes that come into play as well. Laser cutting is now more affordable than ever. You can get a laser cutter at a high school for about a $1,000 price point. And so people like Louise Leakey are making their CAD models freely available so that students in high schools can laser cut cardboard and then reassemble those skulls and figure out and learn again how it has evolved over time. We have some other friends at a company called Other Lab in San Francisco that is making not 3D printers, but 3D milling machines. And so that technology will continue. And then the Smithsonian, as we talked, is capturing some of their collection with this thing called the Charter Collection, which announces in November. And they have this mission to take these 3D captured things and really do more storytelling online. So using some new rendering technologies to tell stories and educate the public about these things that are captured. So stay tuned for what they're doing around this, this X3D project. I think mobile is another way to bring these stories to people. So three-dimensional on mobile. I know CyArk is working on a variety of viewers and technologies for both web and mobile sharing of this digital technology. And as we move forward, we're going to see things like augmented reality, where you take a 3D model and some video, you could put them together, and this is what the commercial world does. They could see where the pipes are underground, but wouldn't it be neat to see what's behind the walls in the castle? See a recreation of some of the history of the people that were locked up inside of some of the dungeons here. And of course, things like this are being democratized as well. These virtual reality experiences that used to cost $50,000 to do a virtual reality cave, you can now, with an Oculus Rift, for a few $100s, have that immersive experience. So things like the Google Glass and so on are things that our research group is working on in a museum, being able to augment this data that's being captured with these stories. And so that's really the end of my talk. The tools are improving. There's a number of companies and researchers. We're really thankful for what CyArk is doing, because it all starts with having the data. We need to capture it. We're making it freely open and available. And now all of these companies, all these researchers have data to work with to really tell the stories to the world. And so I'd like to end with some great storytellers. I think the Historic Scotland organization of using these Hollywood tools to do renderings and tell stories, I'd like to end with that.
In early 2009, the Scottish Government responded to a challenge laid down by laser scanning pioneer Ben Cassira of the non-profit CyArk Foundation to take part in an ambitious scheme to digitise many of the world's most important heritage sites. Scottish 10 would not only record the sites, it would look to share Scotland's technical expertise and foster important cultural and commercial links with overseas partners. To fulfil its part of the global project, the Scottish Government turned to Scotland's heritage agency, Historic Scotland, and its partner, the Glasgow School of Art.
The Digital Design Studio at the Glasgow School of Art has been involved with three-dimensional technology since its inception just over 10 years ago. Early on in the relationship between the art school and Historic Scotland, we started using the terrestrial scanning technology on small projects. And two of the most significant ones, I think, are the work that we did at Stirling Castle, in particular capturing the Royal Palace, which at the time was under renovation, and then another collaborative project that we did at Roslin Chapel to capture the exterior of the chapel as well as the interior.
It's this detailed approach, this innovative technology, that's now being used to drive the Scottish 10 project.
Thank you.
That's such an inspirational talk. I wondered if you wanted to take a bit of time to maybe ask Brian some questions. Just give you a little bit of chance to do that. Then you can put some subjective questions. Nope. Yep.
Try to shout.
Yep.
John? Yes. Hear me? Can you hear me? Mm-hmm. Okay. Hi, Brian. Thank you. A great talk. My question is just to get, I'd be really interested in your view right now of how we start to embed some of these 3D models in browsers. So the way that we're presenting this information seems to also be going through something of an evolution. And
Yeah.
I'd like to hear, you know.
There's a number of things. CyArk is working on this as well. They have a 3D viewer that is based on Java, which of course can run in a browser and has the kind of the horsepower that you need to work and display with 3D data. I think there's one other trend that's happening right now. You're seeing all of the major browsers have adopted this language called Webgl, which is web graphics language. It's a 3D graphics language that enables browsers to do full immersive 3D rendering in a browser. And there's only one browser left, Microsoft, that doesn't support that, which is why you don't see 3D routinely on the web today. However, Microsoft has announced just in the last couple months that their future browser is going to support WebGL. So that will mean 100% of the modern web browsers will have 3D ability built in, no download required. And that's been, I think, the major impediment to this. So we've been investing heavily in WebGL to build technology to bring these massive data sets out to the public, as have many other organizations as well.